Okay, so we have two different measures for center in this course. All right, median and mean, which you should recall these from middle school. The median is the literal center value when the data is lined up from the least to the greatest. So if you line them up from least to greatest and you find the middle, that's the median. The mean is what we consider averages. Usually it's the average value. You add up all the data up and you divide it by the total, just like you are familiar with. That is what we call mean. But the thing is, there's two means that you need to be aware of. The first mean is called mu. Okay? It's a population average. It means that you know the values for every unit in the population. If it's people, you know everyone's height. Okay? And you've averaged everybody's height. Nobody's been left out. And we pronounce it mu. Now, if you're looking at a distribution, how do you find that value? It's the balance point. Okay? So, to understand the difference between mu and x bar, let me show you this. If you have a population, you know, hundreds of thousands of people, like the population of America, it's huge. It's enormous. There's really no way you're going to get the information from every individual in that population. So, in statistics, it's the study of, well, how do you take a good sample from that population that will represent the big population accurately so that we can make conclusions about it from just one sample. So you're going to see this diagram a lot in this course. But here's the deal. Mu is the population mean, which indicates that you have values from every individual in the population and you've averaged them. Now, reality is we don't know mean most of the time. What we know is x bar. X bar is the average that's taken from the sample. Okay, it's a subset of the population. Okay, X bar is what we base our conclusions off of often when we are drawing conclusions about a population, because reality is talking to every individual in the population is probably not going to happen. Okay, so does it matter? Do these symbols matter? Absolutely they matter, and you need to learn them very well now. If you use the wrong symbols, you get the whole question wrong. You have to know which one we're talking about. Are we talking about the population mean? We're talking about a sample mean. It is very important that you know those symbols and you use them correctly. All right, a feature that is not influenced by outliers or skewness is called a resistant measure. It's important vocab for you to know. Now, we have mean and median. So how do they work with resistance? Well, mean is sensitive to outliers and extremes. Mean is non-resistant. Good example of this. If I wanted to know the average Major League Baseball salary, if I looked at the average, it would be way higher than the normal player would get. And that's because there are some players who are worth millions and millions of dollars. Their salaries are getting averaged in with those who are just on the low end of the spectrum. But the result of that is that the mean is not completely a good picture of the population, if you will, because not every player makes millions of dollars. Some do, but that makes the average a little higher than reality would have it. So we call the mean as non-resistant. Now, the median is not influenced by outliers, and we call it resistant. So if you think about it, median is when you line them up in order, least to greatest. So the two extremes, the low extremes and the high extremes, are not included. So those big values or small values don't affect the median. We're looking at just middle. So it's resistant to those crazy numbers that are out there. Now, you can tell things about the mean and the median from the shape of the distribution if you're given the shape. For instance, if it is symmetric, the median and the mean are very, very close. Okay, not exactly equal, but they're very close to one another. And that's an indicator that the mean and the median, that the shape is symmetric. All right? Now, if it's skewed, the median still stays put. It's resisting where the outliers are. If it's right skewed, like this image, the outliers may be on the higher end. Okay? Well, the median stays put, but the mean, the x bar, travels down the tail. What we call chasing the tail. It goes down the tail. So what does that mean? They're not the same anymore, but the mean is greater than the median. Okay? Remember, if it's going to the right, it's positively skewed, so the mean is going to be bigger than the median. Now, reverse that. if it's a left skewed distribution, median stays put. The mean travels toward the tail. Again, this tail is now getting lower because it's negatively skewed. It's getting lower. The x-bar is lower than the median. Okay, so if you know these two values, and that's all you know about a distribution, you can kind of make some predictions about what shape would that distribution be if you knew every data point. So know these values, know these connections. So we always like to say that the mean chases the tail. So if there's no tail, they stay the same right here. But if the tail goes to the right, the mean goes to the right. If the tail goes to the left, the mean chases the tail on the left. All right, so let's talk about quartiles. Let's say we have this list of data, and they're in order from least to greatest. Doesn't even matter what numbers they are right now. This is just to give you a visual. The median is the 50% location, the smack middle of it. Okay, so we have 3, 6, 9, 12. We have 15 pieces of data. So I'm going to count in 1, 2, 3, 4, 5, 6, 7. This is my center right here. That's the median value of this set of data. Now, Q1 is what we call the 25% location, or the first quartile. Now, if this is the 50% in the middle, 25 is the middle of the lower end of the 50% data. So I have 7 down here, so I'm going to find the middle. 1, 2, 3, 4. There it is. This is the middle of the lower 50% of the data. Q3 is the 75%, 75th percentile, if you will. It's the third quartile. It is the middle of the higher 50% of the data, right? So we've identified that. There's the median, Q1, Q3. Now, range is something you've learned before. It's the maximum value minus the minimum value. So what we would say about range, it's not a very accurate measurement of a distribution. We don't really like it because it's not resistant to outliers or extremes. The Major League Baseball salaries, we have some really, really high extremes on that will influence our range. Now, so what do we use? Well, we often use interquartile range, Q3 minus Q1. So whatever this value right here is, we could subtract this value from it, and that would give us an idea of the range of the middle 50% of the data. And this is more accurate because it's cutting off the low extremes and the high extremes. It's a better picture of the range of the data than if you included all of the data. So interquartile range is resistant, while range is not resistant. All right, let's look at this example. McDonald's fish and chicken sandwiches. Okay. Here's the data on the amount of fat in grams in 9 different McDonald's fish and chicken sandwiches. So calculate the median and the IQR. All right, so in order to calculate the median, I first have to take the data and line them up from least to greatest. Okay, so here's my work, but the first thing I did was line them up from least to greatest. And then I look at, I have 9 pieces of data, so I'm going to find the center. Count in 4, the 5th one is my center. That is my median. So 19 grams of fat is the median. Then it says find IQR. Well, to find IQR, I have to know Q1 and Q3. So Q1, I'm sorry, is the middle of the lower 50%. So I find the center. Now, that's an even number, so I take the center 2 and average them. So my Q1 is a 15. Same thing with Q3. It's the middle of the higher 50% of the data. So I take the center 2 and average them. I get 24.5. So to calculate IQR, I take those two values, 24.5 minus 15, and I get an IQR of 9.5 grams of fat. That's all I got to do on that problem. All right, we call an observation an outlier if it falls more than 1.5 IQRs above Q3 or below Q1. So the question is, are there outliers in this distribution? Fat grams. All right, so we got to know where Q1 and Q3 is, and we got to know what IQR is. So I'm going to revisit what we did on the previous slide. Here was our Q1 at 15, Q3 was at 24.5, and then our IQR that we calculated was 9.5. Okay, now knowing that information, we can find out if there are outliers. Now, 1.5 IQRs, that's the first thing I have to do. So I'm going to take 1.5 times my IQR, 9.5, and I get 14.25. Now what I do with this has to do with my quartiles. If it's above Q3, so I do 24.5 plus the 14.25, there's 38.75. So I'm looking at my data over here, and this is like an invisible fence. If the data falls within that fence, like lower than this fence, it is not an outlier. If it's outside the fence, it is an outlier. So I don't have any fat grams greater than 38.75. So there are no high outliers. Now, do the Q1 version. Well, I take my Q1, my quartile 1, and I subtract the 14.25, and I get 0.75 fat grams. Well, that is the low fence. Do I have any fat grams lower than that? No, I don't. So because there are no values greater than 38.75 and none that are lower than 0.75, we would say there's no outliers. So notice there's some mathematical work you've got to show to prove there are no outliers in this situation. All right, so here's data for the amount of fat in grams for McDonald's beef sandwiches. The question is, are there any outliers here? So we have some preliminary work we have to do before we can calculate for outliers. Okay, we got to know what the Q1 and Q3 is, and that means we have to know what median is. So let's put our data in order. 9 through 43, I put it in order. And I'm going to find the median. Now this time there's an even number of pieces of data. So I take the middle two and I average them. I get a 26. Then for the low end, because I averaged them, I'm going to count that 26 right here in my low end because they were averaged. If there was an actual value, I would not include it. But because it was averaged, I'm going to count. Look, I have 6 pieces of data down here, and I find the middle two, and I average. For Q1 is 21. Same idea on the upper end of my data. I have 6 pieces of data. I'm going to average the middle two, and I get 29. All right, so I know Q1 and I know Q3. Now I need to find what is IQR. Well, that's going to be 29 minus 21, which is 8. And the formula says I have to multiply it by 1.5, which gives me 12. So then I'm going to take Q3, the 29, and I'm going to add 12. So there's 41 grams of fat. That's my high fence. My low fence would be Q1, which is 21, and I would subtract the 12, which gives me 9. So this is the low fence. So then I analyze my data. Do I have any sandwiches that have grams of fat greater than 41 or less than 9? Well, 9 is the fence, so it's not less than 9. But do I have anything greater than 41? Yes, there's a 43 right there. So I say a value is an outlier if it's greater than that or less than that. The quarter pounder, double quarter pounder with cheese, has 43 fat grams, which makes it a high outlier. That's how I would answer that. Again, there is work required on this that needs to be shown. All right, so what is a 5-number summary of a distribution? Well, you know this, you just don't know this name yet. 5-number summary is minimum value, the Q1, the median, the Q3, and the maximum. Those 5 pieces of data or information about the data are a wonderful summary of the distribution. You can tell a whole lot from that. So how do we display this? If we have a 5-number summary, we can display it using a box plot. It's pretty simple. So here's one for you. The box it represents the IQR. So the boundaries of the box are the Q1 and the Q3. The line in the middle is my median. Okay, so this represents 50% of my data. Now the box plot, the whiskers sometimes are called. Are lines that draw down to the minimum and the maximum. Now in this example, this is probably the fat grams of the beef sandwiches. We have a high outlier. So that 43 is way out here. And I have a dotted line here to represent that high fence that we calculated. You don't have to have that, but you do need to separate outliers from the rest of the data. So I put that here. And now what used to be the max, which sits right here, the maximum's way out here. So I would then take the next highest piece of data and draw the whisker to it right here. We'll do this again with the chicken and fish, but that's the structure of a box plot. Okay, obviously you need an x-axis that needs to be labeled and scaled correctly to be able to read this. Otherwise, it doesn't make any sense. Okay, so we're going to do, it's called a parallel box plot, but I want to show you how we got there. The 5-number summary that we had when we did the chicken and fish sandwiches, this was our 5-number summary, and there were no outliers. With the beef sandwiches, here's our 5-number summary, and we discovered that 43 was an outlier, and so then the new maximum, if I take the 43 out, would be 31. So here I've constructed a parallel box plot. They're stacked on top of each other. So you can see my x-axis is scaled and labeled. And then over here on the right, what usually is the vertical, I've labeled which distribution is which. So 5-number summary. Remember the box is Q1 to Q3. So 15 to 24 and a half made up my box here with the fish, chicken and fish. The median is the line in the middle. The minimum is the 9 down here. And the maximum, since there's no outliers, is the 33. So I draw my whiskers out there. Now for the beef, looks a little different, but we start the same. Okay, the box goes from Q1 to Q3, so 21 to 29 is my box. The median is at 26. Now the whisker on the low end, there were no low outliers, so I can draw it all the way down to 9 grams of fat. But there was a high outlier, so I need to put a dot out here where the outlier is. And then I look at my data, what's the next highest? The new maximum was 31. So I draw the whisker to that. Now, this is all fine and good, but there are some downsides to box plots. The upside is that you can clearly see if there's an outlier. It's very clear because it's been calculated. That's a bonus of box plots. But the downside is you can't see the modes. You can't see if like one piece of data showed up a whole lot. So if there's like, you can't really see if it's symmetric or not, if it's mound shaped. You can kind of get an idea based on if the box is in the center, but it's not definitive. So the downside of box plots is you can't see the modes. The upside is that you can clearly and very quickly see outliers. All right? Okay, so then the second part of that question after we've done all this work is to compare the distribution. So we're going to walk through our SOX acronym. We want to make sure to use context and use comparison words since we are comparing beef to fish and chicken fat grams. All right, so let's see what this looks like. Chicken and fish sandwiches are slightly right skewed, very slightly, while the beef sandwiches are definitely skewed to the right. Very slightly. This whisker over here on the left is it's not real clear, but slightly right skewed. You could even argue that that's kind of symmetric if you ask me. It's not real clear. But either way, I've mentioned shape, and I've mentioned both distributions in one sentence. Okay? The beef one we would definitely say is right skewed because this outlier is way over here on the right. Second sentence, it appears the typical beef sandwich has more fat grams than the typical chicken and fish sandwich. All right? And clearly, when you have a box plot, it's really easy to see with the medians. Where do these fall? These are like good indicators of what is typical. This one, especially since it's skewed, you want to use median. That's definitely higher than the fat grams of the chicken and fish sandwich. So I've used median as my center. Remember, you can use mean or median, and I'll tell you when to use which in a sec. But in this case, median works well because this is skewed. And it's resistant to the outlier. So I'm going to compare medians. The median, both quartiles and maximum are all higher for beef sandwiches. So it's just showing you that the whole thing is much higher than chicken. Okay? You didn't have to mention the quartiles, but you would at least mention median on that. There's more variability in the chicken and fish sandwiches if you disregard the high outlier in the beef distribution. Okay? So it's just saying there's more variability up here if you don't even consider this. But because this is there, beef technically has more variability. Any way you phrase it is fine as long as you're correctly assessing the variability. The IQR for the fish or chicken is 9.5 grams compared to the 8 grams of IQR of beef. Now, we're using IQR for spread because the beef distribution is skewed. IQR, remember, is resistant to outliers, so it's a better value to compare when you're dealing with a skewed distribution. So we look at our IQR. The chicken and fish is 9.5, this one is 8. They're very close, but they're not. They're a little bit different. And then lastly, about outliers. The chicken and fish distribution has no outliers, but the 43 grams of fat is an outlier in the beef distribution. So as you can see, we have addressed S, O, C, and S. we've used context, and we used comparison words like greater than, higher than, more variability. All those kinds of things are comparison words and phrases that need to appear when you're asked to compare distributions. Okay, so we need to revisit for just a moment the resistant and non-resistant measures, because you need to know which one to use and when. If it's our resistant measures of center is median, okay? The non-resistant measure of center is the mean. Okay? The resistant measure for spread is IQR, and the non-resistant measure for spread is range. Now, why do you need to know this? Well, when you're doing SOCs, you need to determine which measure for C and which one for S you need to use. And it's based on the shape of the distribution. If the distribution is skewed at all, you want to use the resistant measures. If it has any skewedness to it, you want to use the resistant measures. You want to use median and IQR to describe shape and center, and you would use the actual values if you have the data. If the distribution or distributions both are symmetric, you can use the mean for center and the range for the spread. That's legal. But if it's skewed, these are not going to work. All right? Now, let me show you on your calculator quickly how you can do a box plot. So in your calculators, if you want to create a box plot really quick to look at distribution, you would put data in list 1. This happens to be the same points per game in the previous video we did, the basketball points per game. And I want to create a box plot. Okay, so the next thing I would do is go to my stat plot menu. The steps are in the next slide and also in your notes. So I want to turn that stat plot on, and there's the different displays. Now I want the box plot. Now these two right here both are box plots. The one you want to use, however, is this one right here with the dots, because remember, those dots are outliers, and that's really the essential thing we need from a box plot, is to know if there are any outliers present. Without doing all the calculations, it will do it for you. Now, I want the box plot with outliers, so that's done. XList is list 1. And then when I go to, then I would hit zoom 9, so it does the correct frame for me. So there it is. Now, if I want to quickly see my 5-number summary, I can hit trace, and it will start you in the center, and you can arrow over wherever you want to go. So this tells me the median of my data. There's Q1, there's the minimum, Q3, and the maximum. If there had been an outlier out here, let me create an outlier real quick. So I kind of played with our distribution. I created an outlier. So I want you to see, if I trace over, there's Q3, there's the maximum, or not, that's not max, it's the next highest value if I take out my outlier. If I trace over, there's my max at 145. It'll jump back. So notice it doesn't say max here because my max is really my outlier. All that to say, you can quickly see if there's an outlier, and you can also find those values very quickly by using a box plot on your calculators. So here's the keystrokes that I just went through, so you can play with it if you'd like. This does give you the information if you want to do parallel box plots. You would just turn on 2 different stat plots, and they would put them in the same window frame for you. But that's the idea, and we'll see you in class.